Awesome. Thanks everyone. Very honored to be here, and Jean-Nicolas gave a really good presentation. I don't know if you saw me. I was scratching down notes, taking copious notes from some of the points he was making. I thought it was interesting. I was glad to see he had a transition slide where he had that growing complexity slide, and there was a big gap in the 90s and the 2000s, and I thought, oh, we really stopped innovating, and then he advanced the slide and filled that hole, fortunately. So glad to see that there's a constant flow of innovation going on. I'm going to talk at a little bit of even a lot higher level than what was just presented, and talk about some of the things we're dealing with at NERC around North America at a pretty high level, and then try to touch on some of the things that relate to the digital twin concept again at a fairly high level. So let's get right to it. So the first thing that we're seeing is obviously the changing resource mix. That's a buzzword that we've heard around the NERC FERC world for, I'd say 3 to 5 years or so. It started gaining traction as we were seeing, more and more wind, and then solar started showing up. But really, that concept is almost of paramount importance these days. And I think 3 to 5 years ago, folks were still very pessimistic against the concept of, say, 100% inverter-based resources. And it took a lot of industry education and awareness and webinars, things like this, to raise awareness that even under one operating hour or minute or second, if you hit 100%, your energy levels could be at 20%, but your penetration levels could be at 40, 50, 60, 70% instantaneous penetration levels. And reliability is not measured over the entire year. It's measured at any one moment. We ensure reliability across all operating conditions. So as we see the wind, solar, we're now sort of realizing, wow, those are kind of easy, because we've got a good maturity level with wind, and we can predict when the sun's going to come up and go down. But now we throw in battery energy storage and now hybrid plants, and the complexity of the controls and the technologies within those plants, particularly with hybrids, when you've got different mixes of wind, solar, batteries, what have you. Everything gets a lot more complicated, and I think grid planners are going to be faced with some major challenges related to, how do I predict out a 10-year operating case when resources interconnect now in less than 18 months, and the technology may not even exist yet. It creates a really interesting challenge, complex challenge for us to deal with as an industry. So we have our NERC inverter-based resource performance working group that is trying to tackle and address all of these things, and EMT simulations is one of them, which I'll jump into here. Another thing we're seeing is the aggregate levels of distributed energy resources and their impact to the bulk power system. So we have our NERC system planning impacts from DER's working group that is tackling that subject, looking at not any one individual DER, but the aggregate impacts of DERs. And as we all know, particularly solar PV, distributed solar PV, rooftop, or distributed solar plants are becoming increasingly popular across North America and around the world. And I know it's AMO, for example, many areas in North America are also facing some significant challenges related to very high penetrations of DERs and increasingly growing penetration of DERs, that offsetting the conventional bulk system resources, the need to have flexibility and the need to be able to handle that uncertainty, but also having verification that those resources are performing the way we need them to, and developing models, again, to predict what that future case would look like when the system is potentially dominated by these types of resources. And the last thing that we have a sort of a new focus on at NERC, we obviously have our EISAC, which is sort of a real-time data sharing and analysis center that's looking at particularly cyber and physical. And the MINU group is looking at the integration of physical and cyber security with conventional planning, operations, design, system restoration activities, something that has been very siloed in the past. When I talk to grid planners, even grid operators, and I try to have a conversation with them about cybersecurity threats, it's like talking to a wall almost. And I was a planner for many, many years, and never once did I really think about what would a cyber attack look like? How would I maybe potentially simulate that? And what would be the impacts? How could I develop a risk assessment of, if a cyber attack were to happen, what would that look like in terms of a contingency? And more importantly, if a system, we're good at, if we lose our cyber systems, we can bring them back reasonably quickly. If we lose our grid, we have black start capability and cranking paths, and we've got studies that show that we can do that and do that fairly quickly. We're not so good at combining the two of those. If the lights go out and I lose control of AGC and my communications network, I don't think we're very prepared to bring the grid back under that type of condition. So what do we do is the question, and that hopefully we'll have some answers to those types of things in the coming years. But I think it's definitely an area of focus. But back to this subject, I think that hopefully everyone has seen some of these reports or heard about these reports. The infamous Blue Cut fire started in 2016, led to 1,200 megawatts of solar tripping offline unexpectedly. We had the Canyon 2 fire, the Palmdale roofs, Angeles forest disturbances. We issued industry-wide NERC alerts after 2 of those to understand the extended condition of these abnormal performance, and more recently focusing a lot more on the modeling. So 2019, we had a quiet year. 2020, we had the San Fernando disturbance in July. Again, about 1,000 megawatts of bulk system solar PV resources tripping across about 50 resources around a fairly widely distributed area of the Southern California area. And then we also saw some net load increase, which we attribute to DER tripping. This report, combined with some other activities, really highlighted the modeling challenges that we're facing. So we did a joint effort with WEC. We went and grabbed their latest and greatest dynamic models in the interconnection wide base case, which is often used as the starting point to perform planning assessments for your local area. So you might go add in your more detailed models. And again, we're talking about phasor domain models for the interconnection wide base cases, at least today, right? So we took the latest and greatest models with the latest and greatest case. And what we found was bleak, to say the least. About 50% of the wind dynamic models are either obsolete, incorrectly represented, or no dynamic model whatsoever. The same thing with the solar resources. About 90% of the solar resources electrical control models are using a model that every single inverter OEM has said is an obsolete model and should not be used. Those numbers are not 30% or 10% or 50%, particularly solar. It was 90% of the resources have a dynamic model that the OEM strongly does not recommend. That's a scary situation for us to be in, and it smells a little bit like 1996. So I'm hoping that we can have some progress in this area to make these models more accurate, more usable, and I think that's where the digital twin concept can step in. I wanted to highlight, when we start talking about what's the cause of this, why do we see this, and there's many different things, many different factors that play into this, how we got to where we are. The thing I like to just highlight is this reliability guideline that we published in late 2019, which is improvements to interconnection requirements for bulk power system connected inverter-based resources. There's an entire chapter in this guideline that strongly recommends that every transmission service provider go update and improve their interconnection requirements to require during the time of interconnection and throughout the time of interconnection, all these types of models and the things that we're talking about here today, from the phasor domain models all the way to the EMT models and maybe even beyond. That is your opportunity to get the model that you need, at least with current technology, current mindset these days, that you get that model. And if you don't get it during the interconnection process, you don't get it ever, because once the resource starts making money, you're not going to be able to engage with them unless it's in your contract. So when we start talking about these new technologies, new technological advances, things like digital twin, the most important factor is that in the interconnection requirement, that model and any change to that model will be communicated between entities at all times. And I know some entities around the world have driven those types of requirements to really make it clear that we need to understand when things change in the field. It's not okay for a wind plant or solar plant to go out there and change all of their control system and not update their dynamic model associated with it. That sounds like a scary situation. It is an extremely common situation, and we've had generator operators tell us that the owner of that facility demanded that the operator go change all the controls to make them better, which is great. But then they said, well, what about the dynamic model? And the generator owner said, forget about that. It's not important to us. That's a scary situation when a generator operator is telling us that in confidence to say, we have a problem here, right? So we need to improve that area quite drastically, I think. So again, it all comes back to how do we facilitate this data transfer and make this all happen? Like I mentioned, the hybrid and battery energy storage systems are definitely a new area. You look at some interconnection queues around North America, and they are flooded with hybrid plants. So these are, in my opinion, here in some ways, but right on the horizon of the planners having to deal with the complexity of these things. Our dynamic models today really are not well suited to handle hybrid power plants and the different controls, whether it's a hybrid plant or a co-located plant, the different plant level controller that may be wrapped around these facilities. You may have solar, wind battery, solar battery, whatever it might be. Then you have AC connected, DC connected. As a planner, you don't know what's in that case unless you're really innately familiar with that local area. Because if I were to look at this in a base case, I couldn't tell if this was 2 facilities or 1 facility unless I spent hours looking at the dynamic models and trying to understand the plant configurations and all these things. We need improvements in capabilities in the software platforms to be able to wrap these things up nicer. And I think EMT models do a little bit better job with that, even because you're able to sort of click down into these things very easily, tell where the controls are located, all that stuff. With the phasor domain models, it's a lot more complicated. John Nicholas mentioned the growing emphasis of EMT. That reliability guideline I mentioned, point blank, says every newly interconnecting inverter-based resource should have an accurate EMT model associated with it, because you may not have a weak grid now, you may not be dealing with EMT related stuff. You can see they're listed on the screen related to IBRs, but you don't know that 5 years or 10 years down the road you will be. And like we mentioned, with the current mindset and the current structure of agreements, if you don't get that model up front, you're not going to get the model down the road. So you end up using a whole lot of generic models for a modeling situation where you need the detailed intercontrol loops type things to be able to identify real reliability issues, things like weak grid control interactions, that kind of stuff. Generic models aren't going to do anything for us when we're talking in the EMT world. So again, that's where the digital twin could come in and help address some of these problems pretty significantly. So I know I'm running out of time. I'll breeze through a lot of these, but modeling quality is a major challenge. We're seeing the new resource types being introduced to the market. The variability and uncertainty of the study conditions is a major concern. John Nicholas had a really good slide about that. Why does it make sense still to run 10,000 simulations when you know that everything you're studying is completely irrelevant to the conditions that you will be faced with? So I think there will be big advancements, and it was on John Nicholas's slide, regarding artificial intelligence, other things like that, to really drive what conditions do we need to be studying. It's not just the peak and off-peak 2 cases that are important anymore. It's everything in between. The study timelines are lengthening. The interconnection timelines are shrinking. That's a dangerous place for us to be in. And we're seeing a lot more need for EMT. And I mentioned highly leveraged because we're seeing a big demand for EMT studies and a lack of expertise on how to execute those studies in the industry. The everyday planner that comes out of school, maybe the younger ones now are learning EMT in school. I think I was right on that cusp, maybe 10 years ago of being introduced to EMT, but not realizing that it should be a prerequisite to becoming a grid planner, because I think we all need to know how to be running EMT or be familiar enough with EMT studies these days. So we're stretching our consultant capabilities quite drastically as an industry. And even the consultants are saying, you all need to learn EMT studies because we can't run enough studies. We can't hire enough people fast enough to run your studies for you. So hearing that from a consultant is also very eye-opening. Interoperability is a major thing when you go to black box models, real code models. The wrappers around these things need to be interoperable so that we can communicate across software platforms. That is it is a requirement for the interconnection wide base cases. So as we build bigger and bigger EMT models, it's going to become a prerequisite to an interconnection wide or regional EMT type model. So we need to prepare for that. And I know there's activities going on in the industry, CGRI, IEEE, et cetera, to develop that standardization. But regardless of that, data management and the accounting of all of this information as we get super complicated, really large models becomes a major challenge for an individual engineer or a group of engineers to be able to handle with the current technology. So again, we need really seamless, streamlined data management processes to make this all really easy. The biggest way to influence or to sell something is to essentially show the easiest path forward to act, right? And that's what grid planners need today is what's the easiest path for me to be able to execute the requirements that I need to do. So what I'm starting to call it is we need a modeling supply chain. We talk about supply chain is probably the most important thing in the cyberspace these days. We need one of those for the model. And I think that's, again, where digital twin fills that gap to say your modeling supply chain is these things are synchronized in real time. There is no need to account for versioning and changing of control systems, everything, because it's all linked together and it's all synchronized. So again, all of this stuff that I mentioned, the challenges we face, this is only in the planning horizon. I didn't even talk about the real-time operations. I'll let the other presenters cover that in more detail. So I'll leave it at that. And again, I look forward to the Q&A as well.
Well, thank you very much, Ryan. That's very, very interesting. So we'll move next to Miguel Angel Costa Acosta.